So my name is Samiran Datta, and first of all, I would like to thank ROSCON India for giving me such an opportunity to present in front of such a large crowd of like-minded people, fellow researchers, and fellow ROS enthusiasts. So before going into what I'll speak about, I would like to give a brief description of the research group that I represent and the lab that I'm coming from. So I'm an MTech research scholar at IIT Mandi. So our lab, which is called the Drone Lab, comes under the Center for Artificial Intelligence and Robotics, IIT Mandi. And there we do a lot of stuffs ranging from robotics and AI and then integration. And not only that, we have researchers dedicated to quantum communication, quantum cryptography, cybersecurity, and all sorts of cool stuffs. So uh, yeah, so my agenda today is to talk about haptic teleoperation, which is my research field. And we will see what haptic teleoperation is, the challenges that we face in haptic teleoperation, our ways to mitigate those challenges, and some future directions uh, that we might pursue. So when we say haptic teleoperation, the two keywords that come in that are haptics and teleoperation. So let's start with haptics. So can I get a quick show of hands if anyone knows about haptics? Okay, a few. So if I were to describe to a layman what haptics is, maybe getting say, a sensation of feeling of touch or force. Like if I touch this table, I get a feeling that I'm touching this table. So this is a very layman way of describing what haptics is. Now, for some seasoned players in haptics, you may know that haptic consists of two types. One is kinesthetic haptics and one is tactile haptics. So, what is kinesthetic haptics? Kinesthetic haptics is basically when we get to feel the force or the resistance of an object. Suppose I am picking up a box. The force that I'm feeling due to its weight, due to its mass, the resistance that I'm feeling when I'm picking up the box, that comes under kinesthetic haptics. And tactile haptics, on the other hand, is suppose I am touching a silk object, a silk woven cloth, and on the other hand, I'm touching a jute bag. The difference in textures is what makes up for tactile haptics. And nowadays, haptics is quite a hot word in quite a few of industries, especially in, I would say, entertainment industry, gaming industries, when you have these PlayStation 5s, AR, VRs, and all coming with these Joy-Cons controllers, which are based on haptics. Even in Nintendo Switch is coming up with haptic Joy-Cons. And teleoperation, on the other hand, is the concept is very simple. You have an operator here. Suppose you have an operator here in COIP Pune, and you have an agent which you want to control at some distance. Now that distance can be, suppose, a few kilometers. That distance can be a few meters. That can be anything. So the operator here wants to control an agent which is at a few, which is basically at a certain distance away. Now that agent can be a robot. In this case, in my case, at least it's a robot. Now it can be a mobile robot as well as a manipulator. So as you can see, this is a teleoperation setup, basic teleoperation setup. And there we have a communication channel in between, mostly wireless. Nowadays it's all wireless. So the challenges that we face in teleoperation, the basic two challenges that we face in teleoperation are, one is latency and the other one is transparency. Now, what is latency? Latency is basically the delay between the operator side and the remote side. Okay. So suppose we have a critical operation going on, like a telesurgery. So any delay, whether even if it's for a few seconds, that is not quite acceptable. So delay is one thing we have to mitigate, and the second one is transparency. Now transparency is one thing. Like I would put it that way: if an operator is sitting here and he wants to perform an object somewhere else, an operation somewhere else, so the feeling of the operator that he is engrossed in that environment, in that remote environment, is what defines uh, transparency. So now transparency to in order to gain a high level of transparency, you have to have a high level of feedback. Then there are lots of other stuff that it depends on. So I'll be coming to haptic teleoperation, which is my case. So suppose you have a well-defined model of your teleoperative system. Now, what you can do is you can implement a controller, and the basic controller that you can implement is a proportional derivative controller, as we all know. So the the two challenges in haptic teleoperation are stability and responsiveness. Now, when we talk about proportional derivative controller, the way we tune our KPKD gains, we can either keep them low gains or keep it high. Now, both of these classes, low and high gains, comes with their own advantages and disadvantages. Okay. So if I'm keeping it low, one advantage I have is that if it's properly tuned and if I have a low gain, one advantage is that the response, especially if I'm touching an object in case of a haptic scenario, the stability will be greater than if I had used a high gain system. But on the other hand, the disadvantage is that there will be a sluggish response. So if the operator is moving the master robot to a certain distance, the teleoperated robot will take a longer time to cover that same distance. High gain, on the other hand, is fast in that so and is more responsive. So if again the operator is moving the master robot to the uh, the teleoperated robot, on the other hand, will actually try to mimic the action at a faster pace. So it is responsive, but on the other hand, it has this disadvantage, as in that when we are actually touching an object, uh, there will be oscillations due to high gains. There may be oscillations, as in always the cases, and that oscillation will tend to disturb the stability of the system. So suppose again a scenario in which there is a telesurgery going on, and so think for yourself: is it practically possible for a surgeon, suppose, to manually gain switches in between a teleoperation? I hope not. So what have we done is that uh, we have we have proposed a system, an LSTM-based architecture, in which an experienced teleoperator, I would not call myself experienced, but I have certain experience in dealing with this system. So uh, I have teleoperated a robot myself, and I have gathered data from it. So, and I have created three gain classes: one high gain, one low gain, and the other one intermediate in between them. So, and I have fed certain parameters into it, like my position, velocity, acceleration, all of that into an LSTM, so that it can uh, it can understand, it can have a temporal understanding of my approach, of where I am switching the gains, and it can classify the action that the operator is doing into the one of these three gains, and help the operator in real time in switching the gains. So yeah, our contributions here are twofold. One is that we have actually developed a teleoperation system, which includes an Omega 7 haptic device. If you have heard of this device, it's an Omega 7 haptic device. So when we started doing haptic teleoperation, there was no ROS package for it. So we had to develop this ourselves. We have to integrate this. And what we did for teleoperation is that we had used this to teleoperate in simulation a Kinova Gen3 Lite robot, as you can see. And the second, of course, is what I just explained. We propose our LSTM-based gain switching mechanism. So this is the architecture of our ROS Adapt Tele G3 architecture, which is quite a fancy name. So what we are doing here is that is the operator who is moving the haptic device. That is the master device in this case. This haptic device is giving the position, the pose, the position, and the orientation together, as well as some other parameters like velocity, acceleration, and all of the stuff. It goes into it. The pose goes into our ROS node. Now, inside our ROS node, we have a few mathematical implementations on the raw pose that we are getting. As you can see, we have EMA anchoring. EMA stands for exponential moving average. I would not go explicitly into the mathematical side, but consider it as something of a smoothing function on the raw data so that the jitters are filtered out. After EMing, there are certain other things. Anchoring is what is clutching. Now, the basic way of telling it is like, if you have used a mouse, all of you have used a mouse. So what we do is that if you want to put a cursor to one side of the computer, and our workspace is not that huge, so what we do, we move our mouse to a certain edge, and then we bring it up and reposition it so that we can have the rest of the workspace to work with. So that is basically clutching. There are other scaling, deadband, all of these things. Now our LSTM-based KPKD gains come in this closed loop control. Then we provide that to track IK. Track IK basically gives us the inverse kinematics for getting the joint positions, joint angles. And why we have used track IK is that it has a very less execution time. So this track, the joint angles from the track IK goes into a ROS controller, joint trajectory controller, and from that we publish it into our Kinova Gen3 Lite. So, and from Kinova Gen3 Lite, we have a sensor at the end of our end effector. That sensor, if it touches a surface or an object, anything, so it gives us force in 3 axes, Fx, Fy, Fz. Now, what we do is that we normalize that force in one direction, and it gets sent to our haptic device to the user. So this is it. Now, a little bit about our LSTM-based adaptive controller. So it's not a very complicated architecture, as you can see. The execution here is as follows. Like I said, I have trained it on data which is recorded by myself. So the parameters that I have provided are joint positions, velocities, end effector position, velocity, and the force that I'm getting. So acceleration, jerk, and force are some of the other parameters. The output are one of the 3 gain classes that it predicts. The 3 gain classes, as I've just said, high gain class, low gain class, and somewhere in between. So the greatest thing about it is our inference latency is quite low. So it fits quite perfectly into our notion of real-time teleoperated system. So this is our system in action. So yeah, this is the simulation setup. This is me actually operating our haptic device, Omega 7. And this is our simulation setup in which you can see a Kinova Gen3 Lite robot. And what we're doing here is a classic example which is used in many of the literature surveys that I've done. It's a peg in hole task. So the operation is to successfully place the peg in the hole. You can see the clutching mechanism in action. Yeah, so these are some of the performance evaluation in gazebo simulation. The key things to note in this is basically the 41.1% reduction in acceleration RMS and the 51.3% reduction in jerk RMS, which is quite a lot when you are actually opting for a safe and a safe teleoperation. So, and this parameter, which is 23% reduction in path length, is not an explicit, I would say, parameter to judge, but it is based on these 3 parameters that have been recorded. So the interpretation, of course, is this our system, which we have proposed, gives us a smoother and a safer teleoperation. So yeah, the principal insights that we can gain from this is that our proposed teleoperational system improves both accuracy and stability to some extent, especially in simulation, at least. And of course, since we have integrated this whole teleoperation pipeline in ROS, so it can be extended to other robots as well, such as UR5 or something. Right now, we have worked with Kinova Gen3 Lite because we have those hardwares in our lab. So next step, of course, first of all, will be to implement this in hardware. We have actually set this up in our lab, and we are working on it. Incorporate continuous gain regression. Right now, as I've said, we have 3 gain classes: low gain, high gain, and somewhere in between. But what we would like to do is to have a continuous gain regression. And multimodal fusion. Right now, it is all haptics. If we can integrate haptic and vision into it, we can have a greater level of transparency. So yeah, thank you. That's all from my side. And these are my email IDs. If you'd like to talk about anything interesting coming up in ROS Robotics, you're always welcome. This is my LinkedIn profile. And if you want to work in our lab as interns, you are always welcome to do so. Thank you. Have a nice day.